So electrical load calculation. You guys are supposed to do load calculation with me submit on Friday, this Friday, right? You have started this one. So for electrical load calc, my friends, let me see if I can synchronize myself. I always forget to do the synchronization here. Okay, so for load calculation, we did a load calculation, guys, for the lighting panel, receptacle panel, and main panel. This book, as we talked yesterday, they have 5 tenants. Remember that 5 tenants, as well as the 5 tenants, as well as the house panel, and they did calculation for every one of these panels, as well as the house panel. So that's what they're doing. Load calculation for every tenant, as well as the house panel. Load calculation. Okay, a couple of things, guys. You are very familiar with this one, I hope by now. Lighting loads, they always come in chunks. Remember that chunk of lighting loads that we did? The second chunk is going to be the receptacle loads. A third chunk is mechanical equipment loads, tabulated. And the second thing is unbalanced. Why do you think we need the unbalanced load? Because of the neutral. Does that sound familiar to you? We have lighting load, receptacle load, equipment load, and we focus on the unbalanced. Why do we think the unbalanced is? Because of one little thing, is the neutral. So that's kind of the objective of that one. Factors. If you apply a factor, if it's continuous load, anybody have an idea if it's continuous load? What did we do? 125% for certain loads. Non-coincidental loads. Anybody remember that non-coincidental loads? What we did? 220.60, I believe. We picked the largest load and we used it, right? Does that sound familiar to you guys? I hope it is. Otherwise, it's a problem. Okay, so National Electric Code requirement. We know that Article 220 talks, or Article 220, everything you need to know about calculation, almost in Article 220 for calculating the load. A couple of things that we did not talk about in our project, guys, the growth. Remember that growth? Growth, what I would like you to do, I think at the end, you guys, you have to do the growth. A growth, you need to have a future growth, and I believe for our project, I don't know if you guys paid attention to that one. I can't remember what the feeder, 10%? 15% on feeders, and is that what I did? Oh no, that's just for the lighting and receptacle, and also there is a growth. If you guys look at load calculation, okay, here, a good design rule is to allow 10% growth on branch circuits and feeders. So what I would like you guys to do, not the service though, not the service, we allowed on feeders and branch circuit. Can you guys take this into consideration? 10%. 10% growth on feeders and branch circuits. 10% growth on feeders and branch circuits.
Where is that?
This is in page 4 circled. Did I give you guys 4 circled? Please pay attention to it. I don't want you to do anything on the service. Service, I don't want anything on service. Just the feeders and branch circuits. Cool? 10%.
So add 10%.
Yeah, when you come up with the bottom line, just add 10% on the panels. That would be on the receptacle panel, Jeff, and the lighting panel, not the main panel. We don't want the main panel. But so this will provide future growth for lighting and receptacle, and it goes also above and beyond what NEC code book is doing, and good practice electrician. So that's what the consulting engineers, electrician, a lot of people do that. So you guys are familiar with that. We're engineers, we don't go just to the bare minimum. A good increase on every panel, 10 to 15% is a good value to use. The reason why I didn't do it on the main, Aaron, because remember what did we do on the main? We added the future chiller and we added the future 5,000 square foot. It's already accounted for. It's already accounted for in the main panel. It's not accounted for. It's also accounted for in the receptacle panel. But on the feeders, let's put 10% on the feeders. Cool. Any question, guys, about this one? Growth, future growth. So 10 to 15% is not out of the ordinary. So when we do all this one, you guys remember how out of the outcomes of this load calculation is really two things, mainly two things. is to size the feeders and the branch circuits, right? The outcome of load calculation every time is to size the feeders and the branch circuits. When we size a feeder, feeders don't sit up in the air. We always land feeders in where? In panels. So you need to land feeders in panels. So then you see have the minimum loads as we did, procedures to use calculated. There's calculation for electrical loads. We did, I'm not going to go through all the step-by-step guys that we did, all Article 220. But your ultimate solution for the load calculation is, for example, here's my panel here, and to get all the other panels that's tied to this panel, right? That's the ultimate solution, right? So you need to size the servers and all the feeders, The branch circuits, guys, I have a one standalone lecture about branch circuits. Can I have thumbs up from every one of you guys? Tell me that, Chad, we fully understand how to do the service and the branch circuit, because it's very important. Service and service and feeders. For branch circuits, what I'm going to do, guys, tomorrow, I'm going to take 6, 7 different type of branch circuits and walk you how to size the branch circuit for them. The feeders, we just went through the whole receptacle panel, lining panel. Any comments, guys? Any questions about that? The feeders and the branch circuit? Energy code. We didn't talk about the energy code, guys. Let me just tell you, what was the volt ampere square foot for commercial building? 3. Thank you. So the NEC code, take this. NEC allow you 3 volt ampere square foot. That's your allowance, right? Or the volt amp of your fixture, whichever is bigger. Now take this. Here's the NEC. Now you go to the energy code that we in Minnesota, as well other states, have to adhere to. Energy code. Energy code. I believe right now, I think it's 1 volt amp or even less. 1 volt amp per square foot. Look at this. Look at this. Do you guys see that? So the NEC allows you 3 times more than the energy code is allowing you. 3 times. 3 times. That's why, Darren, when we designed this building, you're going to find that the volt amp that we got from the NEC code book is at least twice as much as the volt amp from the fixtures, since by the way, we're going to be using LEDs and a couple of other things. Everybody understand how the energy code will force you, to go even lower. But do we design the system based on the energy code or based on the NEC code? NEC is the design, NEC for safety. Now, you end up with a panel that size. So take this. If you size based lighting panel, if you size based on the energy code, this panel is 100 amp, literally. If you size based on the NEC code book, this panel is 300 amp. So 2 to 3 times more. Does that make sense? But we adhere to the NEC code book. But in the back of your mind, guys, I can't emphasize, in the back of your mind, when you're doing all this calculation, that's why if you end up, take this. If you end up, for example, with 200, let's just say 230 amps panel, 230 amp panel. Should I go up or should I go down? Now, knowing that this is a lighting panel, and you know for a fact to meet the energy code, you have to go much lower than that. I can, as an engineer, I can go lower, and I feel comfortable going lower. Does that make sense? Can I just get you just to think of the energy code is a comfort zone for you when you do, instead of going, say if I go always up. For me, I want you guys to go always up. Value engineering, when you sit and look at the big picture, you start going down because, I know the NEC code will give me this, the energy code give me this. So if I end up with an odd size number panel, maybe I should go down because I know for a fact my lights are going to be lower than what I calculated for. Can I get you guys to understand this concept? Cool? But with me, all what you guys do, all the sizing, everything that we're going to size is based on what? The 3 volt amp. Okay, so that's what I wanted to mention. Okay, so everybody has been there in this table 220.12, guys. That's give you the volt ampere square foot. And in a commercial building, we say 3 volt ampere square foot for our commercial building. We talked about show windows. You guys remember that show window? You allocated 200 volt ampere linear foot, right? We talked about this one, track lights. We talked about track lights. We allocated 150 for every 2 feet. Remember that? Everybody remember these? So this is just to review. quick review. So everybody is familiar with that one for track lights. For track lights also, they want you guys to have a receptacle. For show windows, they want you to have a receptacle above each 12 feet section so you can feed these track lights. That's just an outlet. Here to the allowances, required sufficient capacity. So they talk about the track lights, so you can't overload your track lights more than, the problem with the track lights, you can add more heads to it. So if the track light says it's rated for 15 amps, can you keep just adding heads until you pull 20 amps out of it? No, you can't. So that's what this basically talking about. Nonlinear loads. We have a nonlinear loads. Now, Andrew, my friend, you are my friend today. I know it's Tuesday. Nonlinear load. You're going to assume the following. All your lighting loads and receptacle loads are nonlinear loads because of the computers and all the electronic equipment that you're plugging. That's our assumption. Who cares? That's why up to, as I told you guys, up to 225 amp panels, full neutral, full neutral. You can even go as high as, I would say, definitely up to 225 amp, full neutral. Higher than that, you start derating the neutral. Did you guys hear me? Good 225 amp panel, 225 amp panel. So I equal or less to this, go full neutral. What's the problem with harmonic? Harmonic go in the neutral and they burn the neutral. They don't add up to zero like everything else. They are offenders. They are the bad boys and bad girls. So they don't add up to zero. Well, that's why if you have phase A, phase B, phase C harmonics, third harmonic on when they add to the neutral, if you have 10 amps, and instead of adding to zero, like a three-phase system should work, they add up to 30 amps. Who cares? Now you have you have a neutral that's actually burned. So to avoid this, can I get you guys to understand if your panel is 225 amp panel, full neutral. After that, most likely lighting panels, guys, go on receptacle panels up to 225 amp. Higher than that, it's always mechanical panels, right? Or service. With the service, when you put linear load and nonlinear load together, they offset each other. So if you can just get up to 225 amp linear load, that would be great.
And you, for the load calculation that we want Friday, if you just want us to get like the math part done?
Yeah, thank you. Do the math part is done, and right underneath is full neutral because of harmonic. Did you guys hear me? For the receptacle panel and the lighting panel, but for the main panel though, your main panel is going to be more than 500 amp, right? So that's we do it.
But as far as like putting in all the receptacles for this building, you want us to do that or wait until we have to just input the stuff?
Oh yeah, thank you. Input the stuff that I gave you from the sheet for the time being. Yep.
Okay.
Input that stuff, the data that's given to you, and later on when we finish the design, you're going to go review it, and you're going to be very close.
Okay.
Cool?
Yep.
So that's good point. Okay, so then general lighting load. For general lighting, you take the lighting load that's coming from this table, guys, which is 3 volt per square foot. Are you familiar with that one, right? 3 volt per square foot. Or you're going to compare it. You're going to determine the actual connect. You're going to take the largest of these two. You guys, isn't that what you did with me? You're going to take the connected load, the actual load, and the load that's coming greater of the two values of the calculated load as well as the connected load. Everybody understand that? So 3 volt amp times 30, so I'll give you 30,000 kVA. Then you add all your fixtures volt amp. If they are less than 30, what do? Stick with 30. You guys have done that one with Excel, and we've done it in the example, so I feel comfortable with this. So this is for general lighting for the area. The storage area, they allow you is 0.25 volt amp per square foot for storage area. Per square foot. That's storage area. Now here's what I do carry. If I have a storage area in the building, you guys have a storage area. I don't split hair. So I take the whole outside perimeter of the building multiplied by 3. Now, can you go to the storage room, take the square foot of it, multiply by 0.25, the office area, multiply it by 3, and divide it into area per area? Yes. Yes, you can. Typically, guys, most of us, if the building is 80% office building, right? The building that we're dealing with 80% of is in office building. The 20% is just hallways, right? And support areas. Apply the 3 volt amp per square foot for all of that. Can I get you guys to understand that one? Now, can you split the area into the office building into office area and shipping area and hallways and all this good stuff? Yes. Is it worth it? No. Cool. So that's what I want you guys to understand. We talked about the show window, linear foot. For the show window, you're gonna allocate this amount of volt amp or your linear foot. Receptacles. So that's the first thing that they talk about. I want to remind you, this is taking a project in the book, and which we have a drugstore. We have what else? We have an insurance tenant, a bunch of others. Receptacles. You multiply 100 volt amp per the number of single or multiple receptacle, 2 straps on one, right? Remember that one? And we have an AC receptacle required to be within 50 feet within sight of the AC systems, the air handling unit. This does not apply to it. Remember that receptacle you have to have within sight of the air handling unit and HVAC equipment. You're going to see how this author is dealing with it. I think it's giving it 1500 volt amp. That's judgment, 1500 volt amp. I typically use, guys, 180 volt amp and apply the rule for it. So here's the receptacles. Everybody, I like this because it's graphic. Here's your 180, 180. Now you start putting 90, 90, 90, and 90 here, right? 360 and the same thing. You still 90, 90, 90, 90. Everybody's familiar with that one? The quads are counting at 360. The duplex and the single are counted as 180 each. Cool? I thought the graphic is really cool here. So that's receptacles. Sign. Remember the sign we said? You guys did that one for me. For the sign, we use 1200 volt amp and we multiply it by what? 1.25. That becomes a continuous load. You have to have a dedicated branch circuit for the sign. So later on, when you start circuiting Kerry, what are you going to do wherever the sign that says "Welcome to Hallberg Engineering"? You're going to dedicate what? A 20 amp circuit to it. Cool? That's not a big deal. 20 amp circuit dedicated to it. And what's the load? 1200 volt amp. Equipment. This is all for equipment and appliances. Equipment for appliances, this is the article that you're going to do. For motors, this is your article. And for HVAC equipment, this is your article. And I remind you guys, for HVAC equipment, this is where you got the non-coincidental loads. And here is where we took 1.25 times the full load current largest, plus everything else, plus all, right? Appliances, we add them at 100%, 120%, 100%. If anything is 100% for appliances, and this is 125% appliances in the kitchen. Remember that what we did for appliances in the kitchen, we applied the rating factor for it too, if it was in the kitchen. What is it, 70%? HVAC equipment at 100%, these are at 100%. These are 1.25 times larger. This is at the rating. The rating if it's in the kitchen. The rating if it's in the kitchen. Any question, guys, about this? Any comments? Any questions about that? Okay, so that's yes.
A question for you.
Yeah.
I don't know if you know this yet, but
Go ahead.
general lighting load, we have general lighting load at square foot, 3 times 3.5, and then we have a second one that's half. Is that the unknown?
These are the unknown. Yeah. Is it 3.5 or 3 for volt amp?
Is it 3 for residential?
We don't want a residential. Was it commercial? Was it 3.5? Okay, thank you. 3.5 for commercial. Okay, we thought 3. Okay, so HVAC equipment, this is heating, cooling, and ventilation. Hermetic motors, guys. For the drugstore, we have the hermetic motor, basically the compressor. A couple of things about the compressor: they give you rated load amps, and you run with it. Inside the rated load amp, sometimes of course you have to have a voltage, you have to have the evaporator and the condenser, and all these will be converted into volt amps as you add them. You guys remember how we get you the rated load amps? rated load amps of the equipment, and we multiply it by the volt amp, and that's how you got your information about this equipment. Okay, here's an example of AC units. So here's the amps that you have, and here's the amps for, you have the condenser and you have the motor compressor. From these two amps and the voltages, you find the volt amp, right? Same thing in the outside unit. You have the indoor unit, you have the heater, and you have the evaporator full load amps. And from these, you find the volt amp for each these all these systems, right? All these equipment, you take the full load amp and you add them. Any comments, any questions? Any comments, any questions? And I know we've done that, so summary of drugstores and volt amp. This is interesting. In the drugstore, guys, this particular project, here's the connected load for the drugstore. Is this then that here's the NEC code book. So the NEC came up, the NEC load allowance 4185, and the connected load is 4155. So which one do you think is going to choose? We're going to choose the largest. We're going to choose the largest. That's what we did, guys. You take the connected load and compare it to the actual load, and you choose the largest. For the storage area, the connected load was this, the volt amp for all the fixtures is greater than the NEC code. The NEC code is giving you this. So which one are you going to use? The connected load, right? So whichever is larger, you're going to use either NEC or the connected load. Can I have thumbs up, Chad? We fully understand that one. Yes, no? Andrew, my friend, you guys go? Okay. So calculate 180 volt amp. This is just going through the project that they have and how many receptacles they have in each one of them. I want to show you, the last thing I want to show you guys on this. Any question about this? I know we went through the load calculation for our project. I can't emphasize, guys, this is another set of eyes looking at the project. Another set of eyes looking at the project. So I want to show you before this one. We talked about this. Here's the commercial building. We talked about the office building, 3.5 volt amp. You guys are familiar with this table. We went through it many times, so I'm going to skip on that one. Okay, here's my favorite. If you guys look at this, this is linear connected load in the, this is what you're going to do with me later on. This is in the drugstore in the office. They have style I, G, G emergency, E2, E, and here's the number multiplied by the volt amps. So here's the, I'm sorry, this is how many of them. So here's the volt amp, multiplying this by their number equal this, right? Can you see that? The volt amp for all the types of the fixtures that we're doing. All the types of fixtures, and they're adding them right in here. Non-continuous load, they're adding the non-continuous load. The reason why they have these as non-continuous load, I think they're emergency lights here. So here's the load that you're going to be sizing at, 2494 volt amp. So the continuous load, the reason why I separate them continuous, non-continuous load, because you're going to multiply the continuous load by what? 1.25. The non-continuous what? 100%. Any comments, any question, what you guys going to do for your project? Darren, so you're going to have all your fixture here in a list with how many of them you have, multiplied by the volt amp, and they're going to compare them with the 3.5 volt amp per square foot. They did this one for you in the book. Cool. Okay, so I just wanted to flash this one. And more lights in the drugstore, the same thing. I want to talk about this one for a second. This is how they did the load calculation, guys, for this project. The load calc for this project. It's very, very similar to what we have done. Can I get you guys to look at the general light? This is for the drugstore feeder. General lighting, 220.12. I have how many fixture count? The square foot is 1395 multiplied by 3, and give me a calculated NEC code book of 485. Connected load, all the fixtures are 263, and total, this is my total, 485, and continuous load 485, and the neutral is going to be 485. I can't emphasize here. So this one is your total load for the light, and it's going to be also in the neutral. Can you guys see that? This is and then Your connected load, look at the connected load, how it's smaller and continuous, all of it is continuous. What does continuous mean? So you're going to multiply it by 1.25. Can I get you guys to understand how they did their system and this load calculation? That's it. So that's your load calculation they did. For the storage area, they did the same thing. Instead, they took 0.25 times the square foot of the building of the storage area. They did the same calculation. Receptacles. They have 120 receptacles, multiplied them by this amount, right? And they added them by the volt amps. They added all the other receptacles. If it's an office building, you have to apply. They didn't apply the demand factor on them because they're less than, if you can see, they're less than 10,000 square foot. The AC equipment, guys, they take the full load amps and multiply it by the voltage that they have to get you the total, and they added it. If it's not a neutral load, they don't put it on the neutral load if it's not a neutral load. So without further delay or important, this is another way of doing the load calculation. I would say 95% of what they did, we did, guys, slightly in a different format. Any questions, any comments? Any questions, any comments? So what I would like you guys to do is to go through this book and please do the calculation. I want you to get out of this class knowing how to do all the calculation, load calculation that God created. Okay, the final. Here's they added all the continuous load after they multiplied by 125 and the neutral. So these are the two values that they did. So this is how you're going to size your phase A, B, and C, and this is how you're going to size your neutral. Any comments, any questions about this? And you guys have done that with me, and you are doing it, and you're working on it too. Okay, that's basically all what I wanted to show on this this presentation. Any comments, any questions? Aaron, does it make sense? A lot of load calculation, man. You're gonna get, and tomorrow and this week I'm gonna be doing load calculation for other type of buildings. So we're gonna get you a lot of load calc. Starting tomorrow, we're gonna do a few other places too. Okay, in this